Welcome to the Explainer. Today, we are diving into one of the most fundamental and honestly one of the most intuitive concepts in computer science, greedy algorithms. We're going to break down what they are, see where they shine, where they completely fall apart, and most importantly, how you can absolutely nail these questions on an exam. Okay, let's just jump right in with a problem you've probably solved 1,000 times without even thinking about it. Picture this. You're working a cash register, and you need to give someone $5.20 in change. You've got a drawer full of euro coins. How do you do it using the fewest coins possible? Seriously, what's the very first thing you do? What's your gut instinct? So here's our game plan. We'll start with what a greedy algorithm even is. Then we'll use that coin problem as a bit of a cautionary tale. After that, we'll tackle a scheduling puzzle to see how to find the right kind of greedy. We'll look at a really famous application called Huffman coding, and then we'll wrap it all up with a solid strategy for your exams.
All right, first things first, what exactly is a greedy algorithm? Let's get to the core idea.
You know, at its heart, a greedy algorithm's kind of an optimist. It builds a solution one little piece at a time, and at every single step, it makes the choice that looks best right now, in this very moment. It doesn't worry about the future, and it certainly never looks back to second-guess its past choices. It's all about that immediate, obvious win.
And this brings us to the central challenge, the real puzzle of any greedy algorithm. It focuses on making a locally optimal choice, what's best for this one step. But what we really want is a globally optimal solution, the absolute best answer for the entire problem. So the million-dollar question is always this. Does making a series of easy, short-sighted choices actually lead us to the best possible overall outcome?
Okay, let's put this idea to the test and go back to that coin problem we started with. This is a perfect example to see what we're talking about.
So the greedy strategy, your instinct, was probably to just grab the biggest coin you can, right? For 520 cents, the biggest coin is 200. Great, let's take one. Now we have 320 left. The biggest coin we can take is another 200. Now we're down to 120. Next biggest is 100, leaves us with 20, and a 20-cent coin finishes the job. That's 4 coins. And you know what? For the Euro system, that's not just a good answer, it's the perfect answer. It works.
And this is so important for any exam or interview, you can't just stop there. You can't just assume this simple strategy is always correct. You have to ask this question. Does it work because the strategy is brilliant, or did we just get lucky with this particular set of coins? So let's throw a little wrench in the works. Let's imagine a brand new, kind of weird coin system where the coins are worth 1, 3, and 4. And our target is to make change for 6. Simple enough, right? Well, if we follow our same greedy rule, take the largest coin possible, what happens? To make 6, the largest coin we can grab is the 4. Okay, so we take that. We have 2 left to make. The largest coin we can take now is a 1. And then another 1. That gives us a total of 3 coins. Seems reasonable. But it's wrong. The best solution is to just use 2 3-cent coins. That's only 2 coins. And boom, there it is. This is a classic counterexample. It proves that our greedy strategy failed. The locally optimal choice of grabbing that 4-cent coin first actually blocked us from finding the true, globally optimal solution. So the big lesson here is that the greedy idea itself isn't broken, but our specific greedy choice, take the biggest coin, was flawed. For some problems, we just need to find a smarter, more clever greedy strategy. So let's see how we can do that with a new puzzle. All right, new scenario. Imagine you have a list of events, all with start and end times. You want to attend as many as possible, but you can only be at one at a time. What's your greedy strategy? Do you pick the shortest events first, maybe the ones that start the earliest? Or what about the ones that end the earliest? All 3 sound kind of plausible, don't they? Well, it turns out the first 2 are traps. Think about it. If you pick the shortest event, what if it's a tiny 30-minute meeting right in the middle of the day? It could block you from attending 2 different 2-hour events, one before and one after. Not good. And picking the earliest start time, that's a trap too. What if that 9 a.m. event is an all-day conference? You've just locked yourself into one event and missed out on a bunch of others. So the winning approach, the one that's actually guaranteed to be optimal, is the third one. The correct greedy choice is to always pick the next available event that finishes as early as possible. And the logic here is just beautiful. Why does this work? Because by picking the event that gets you done and out the door the fastest, you are maximizing the amount of time you have left to schedule more events.
It's a greedy choice that always leaves your future options as open as possible. And in this case, that's what leads to the best overall schedule.
Now, this isn't all just for abstract puzzles. Let's look at a famous real-world algorithm that uses a brilliant greedy strategy, one you probably use every single day without even knowing it. We're talking about Huffman coding.
Huffman coding is a cornerstone of data compression, like in zip files. The main idea is super smart. Why should a common letter like A take up the same space as a rare letter like Z? It shouldn't. So Huffman coding assigns shorter binary codes to frequent characters and longer ones to the rare ones. And it figures out the best possible codes using a simple, greedy method. So here's the brilliant, greedy choice. At every step, you simply find the two characters or groups of characters that have the lowest frequencies, and you merge them together into a new node. That's it. For our string, B and D are the rarest, so poof, we combine them. Now we look again. The two lowest are C and our new BD group, so we merge them. You just repeat this simple, greedy step until everything is merged into one single tree. This tree gives us our codes. If we say going left is a 0 and going right is a 1, we can just trace the path from the top to get each character's code. And look at that. A, our most frequent character, has the shortest code, just 0. And B and D, the rare ones we merged first, they got pushed to the bottom and have the longest codes. This is a provably optimal result, built from one of the simplest greedy rules imaginable. Okay, let's bring this all home. How do you take all this and turn it into a winning strategy for an exam or an interview? How should you actually think through these problems? Here is your 3-step playbook. Step 1, clearly state your greedy choice. What's the simple rule you're going to follow? Step 2, formulate the actual algorithm based on that rule. And step 3, this is the money shot. You have to prove or disprove it. You either show why it's always optimal, or you find that one, single, beautiful counterexample that breaks it. Justification is everything. And please, please avoid these common pitfalls. The number one mistake is falling in love with your first idea and not even trying to break it. You have to be your own biggest critic. Actively hunt for that simple counterexample. And if your strategy does work, don't just say it works. You need to explain the logic, the why behind it, just like we did with the scheduling problem. And that's our look at greedy algorithms. It's such a cool concept because it really makes you think, doesn't it? Where else in life are we making these seemingly smart, locally optimal choices that might not actually be the best for us in the long run? It's a powerful reminder that sometimes the most obvious path isn't the wisest one. Hope this helped make it all a bit clearer.